Hey physics, it's Horner, and this is number 21 through number 38 for the concept questions for both circular motion and for torque. Suzie Spacewaker, so here's Susie, she's out here, is in space beside a rotating space station, and it's rotating. Both she and the center mass of the space station are relative rest. So it's not rotating here, and she's just sitting here, so she's watching it. If the space station is in Earth orbit, so the space station is going around the Earth, then she is also going around the Earth because she is at rest compared to it. So when she looks at it, she doesn't think she's moving. But when they look through the space station window back at her, they can see her moving very quickly across the face of the Earth. So that's really all they wanted you to do is just see that she is also in Earth's orbit. For number 22, torque is defined basically just as the force times the lever arm length. This should be lever arm. So here's our lever arm, or our torque arm. Sometimes they call it that. And we multiply that times the force. So we remember that torque, tau, is equal to force times the lever arm distance. For number 23, it says, suppose you try loosening a nut with a wrench, but the nut doesn't give it all. You increase your chance of success if you, now there's several things you can do. You can have a friend help you pull on the wrench, so that would increase the force. And if we know these because we can remember the equation, torque is equal to force times the lever arm or the distance. So if I have a friend help me, I've increased the force. For the next one, be sure to exert the force perpendicular to the lever arm. So we know that we want this to be perfectly perpendicular to the lever arm, or 90 degrees. If you do that, then the cosine of the angle is 1. And that's essentially what we want. Next one says exert a larger force. So once again, we've increased the force. For the very last suggestion, you could extend the lever arm. If we make this lever arm even longer, so we've made D longer, you've made D bigger, and if you make D bigger, you make the torque bigger. And that is number 23. For number 24, to turn a stubborn screw, it's best to use a screwdriver that has a, most people are used to screwdriver handles that look like this, but this is a different type of screwdriver handle. It allows you to have a much further radius from which to turn. So if you notice, from here out is much longer than from the center of this screwdriver over to here. And these are the same size handles, so relative to each other, they really do look like that. And you'll notice that this is called the torque fix, so this one actually really does a good job. So we want one with a wide handle, not one with a very thin handle. So we're looking at the handle from the center of the handle out to the side. For the next one, it says add a health ball, Felix Flex. So this is Felix Flex. Felix is the man. Finds that pulleys on an exercise machine are not circular, but are cams. They're oval. At different orientations, the cams will actually provide different lengths of lever arms. So you'll see that the lever arm, when it is here, is very short. As it gets as he pulls it further and further, you'll notice that the lever arm gets much bigger as it continues through. The force is required to produce a given torque. So the cams provide different forces, and so you get a different torque. So those are the two things you need to know. Two people sit on a balanced seesaw. When one person leans toward the center of the seesaw, that person's end of the seesaw, it should lift up in the air, because what they're doing is when they lean forward a little bit, so if this person was to, well, you know what, let's have the other person do it. If this person leans in a little bit, then this side will rise, and it's because the distance from the center to where they are originally is here, and when they lean in, will probably be a little bit further forward. So if they both have the same mass and this person leans in, then the distance is less, so the torque is less, and so you can kind of see that type of thing happen on this side to this person. For number 27, it says the center mass of the solar system. So here is basically, this is the sun, and this is where the center of the sun would be. The center of the sun over different periods over the years, actually you'll see that it makes these kind of circular motions. So the sun actually wobbles back and forth, and it wobbles because the planets are moving around it. And if you have all the planets on one side, or if you have a couple big planets on one side, a couple small ones on the other, the sun will actually be closer to those bigger planets than it will to the smaller ones. So you'll see over time the sun kind of wobbles back and forth. That's how we can tell whether or not a star, when you look at a star, if the star doesn't move, we know there's no planets. If the star looks like it's here and then seems to move over here and then move back and forth over time, then we know that there are planets tugging on it. So when the planet is here, it pulls the star that way. When the planet's over here, it pulls the star this way. So we actually see over time a wobble. You can't just look at the star and see it going back and forth. The star actually very slowly goes back and forth, so they look over at a period of many, 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 many months. And that's the key. So for number 28, when a wrench is slid spinning over a frictionless tabletop, its center of gravity follows, so you'll notice that this one is spinning, so it's spinning counterclockwise, and as it's spinning, it is also moving to the right. And you'll notice that the center of gravity of that follows along a regular straight line path. So it actually does make a very, very straight line, and that's the center of gravity of it. So that's where all the mass would be centered, or they call that center of mass sometime. If you try to touch your toes while standing flat against the wall, you will probably fall over. You should try this. So pause the video, get up, go try it, and then come back, and we'll talk about why that happened. So I will wait here a little while. Okay, good. You're back. Your center of gravity will be outside your support area. So when you bend over, typically your rear end goes this way because your front end is coming down this way. And so you end up kind of making this type of figure. Okay, so this would be your head, this would be your feet, this would be your hands. When you stand against a wall and you try to bend over like that, you can't, because this part of you cannot go backwards and you end up hitting your head on the floor, or you put your hands down and you block yourself. So you probably noticed that when you just did it, because I'm sure you got up and tried. Number 30, where is the center of gravity of a softball bat located? So we talked about this one in class a little bit. Notice that the center of mass, or the center of gravity, is really in the bigger end of the bat. So if I tried to balance that bat, it would be on that more massive end. So it would actually balance right here. So I'd have to turn it flat left to right and try to balance it. So I could have my baseball bat. That's a really bad baseball bat, I realize. But if I tried to balance it on a knife edge, I would have to do it right there. Next question is number 31. The center of mass of a human body is located at a point that changes as a person bends over. So this person, when they stretch up, their center of mass rises, and then when they bend over, their center of mass actually comes outside their body and is just below. And you'll notice that the rear end of this person went backwards because the heavy part of the person went forwards, and so you want the center of mass to be right over the feet. If it's not, you'll fall over. The other interesting thing is, if you look at these two people who are about the same height, a woman's center of mass tends to be closer to just below her belly button. And here's the belly button for the gentleman, and his is above. It's because men have very broad shoulders and women have very broad hips. Little kids, their center of mass is actually much higher, so they topple over a lot more. So you'll see a kid running and all of a sudden, boom, they plop down. And they don't fall on their rear ends. They actually will go flying forwards. It's because they're a lot heavier on the very top because their legs are short and their torsos are long. So that's a little bit more information for that one. This talks a little bit more about why men have a higher center mass than women do. An object thrown into the air with a spin rotates about its center of gravity. So if we took that wrench and instead of scooting it across the table and spinning it, now we're throwing it and spinning it. And you'll notice that it makes that typical parabolic motion, but you'll also notice that it spins about its center of mass, which is kind of cool. Number 33, when you carry a heavy load with one arm, why do you tend to hold your free arm away from your body? So you'll notice this person, he's trying to hold this out a little bit and he's actually leaning a little bit. And it's because you're trying to change the center of gravity of your body and the load. So if you put somebody on your back, you'll lean forward because you're trying to keep the center of gravity over your feet. If you put a bag on one side, your center of gravity shifts, so you tend to put your arm out. This lady's carrying some books close to her chest, so you'll notice that she leans back in order to keep her center of gravity above her feet. If she didn't lean back, the books would be out here and she might trip and actually topple over, which would be bad. Number 34, the long heavy tail of a spider monkey, so there's the long heavy tail, enables the monkey to easily vary its center of gravity. So it can raise that tail forward, have it come over its head. That would make its center of gravity more in the middle. If it puts it down, then it comes back a little bit. So you can do a lot of different things because of that. Number 35, an object will fall over if its center of gravity is not over its area of support. So we notice here that if I have this plumb bob, so I've attached a little tack to a weight and a string, and as long as this string stays behind this front point, this thing will not topple over. So in this picture and in this one, we notice the string is still right at the front edge. Here, you'll notice that the string is in front of the front edge of the box, and because of that, this is where the box started, and now it is actually toppling over. So that's what we call toppling, and that's why it happens. For number 36, if an object is in stable equilibrium, so this one is in stable equilibrium, any displacement, so if I try to bump this thing and knock it over, it actually raises the center of gravity. When it does that, the thing tends to fall back down because the center of gravity wants to come back down. For number 37, if I have an object that's in neutral equilibrium like a ball, any displacement does not change the center of gravity. So if you think about the ball, when I roll it, that ball's center of gravity will stay the same, so it will not raise nor lower it. If something is in unstable equilibrium, remember we said that if it's not in neutral, if it's in stable, it will raise the center of gravity and then it'll fall back down because it wants to have the lowest center of gravity possible. This one, if it's unstable, any motion of this one will make its displacement should lower its center of gravity, so it will fall down. So we're trying to get this to be the lowest center of gravity possible. And that is number 21 through 28 for your concept questions for circular motion and torque.